ಓಕೆ ಯೂಟ್ಯೂಬ್ಗೆ ಹೋಗಿ ಇವಾಗ. ಯೂಟ್ಯೂಬ್ಗೆ ಹೋಗಿ
ಅಷ್ಟೇನಾ?
ಅಷ್ಟೇ, ಡನ್.
ಯೂಟ್ಯೂಬ್ ಇಲ್ಲೈತೆ
ಇಲ್ಲಿ
ಸ್ಟುಡಿಯೋ ತಾನೆ.
ಆಫ್ಟರ್ 30 ಸೆಕೆಂಡ್ಸ್ ಬರುತ್ತೆ, 30 ಸೆಕೆಂಡ್ಸ್ ಡಿಲೇ ಇರುತ್ತೆ. ಎಸ್ ಯು ಆರ್ ಗೆಟಿಂಗ್. ಹಾಂ ಸರ್ ಇದೆ. ಸೊ ಒಂದು ನಿಮಿಷ ಬಂದೆ ಸರ್. ಮೇಲ್ ತಗೊಳ್ಳಿ. ಹಾಂ ಬರ್ತಾ ಇದೆ ನೋಡಿ. ಅಷ್ಟೇ, ಆಲ್ರೆಡಿ ಲೈವ್ ಅಲ್ಲಿ ಇದೆ ಈಗ. ಲಿಂಕಿಗೆ ಅಲ್ಲಿ ಶೇರ್ ಆಪ್ಷನ್ ಇದೆ.
Hello, am I audible to all? Okay, good morning one and all. So we are on exact time at 11 a.m. We are on right track. Good morning all of you. Today's session will be handling by Dr. Arjun Mudlapur, a postdoctoral fellow at IISc. So it's an immense pleasure for me to introduce him. Arjun M completed his PhD in electrical engineering from National Institute of Technology, Surathkal in 2019, and is currently pursuing his postdoctoral fellowship from Indian Institute of Science, Bangalore. His areas of interest are development of analytical models for power converters and photovoltaic systems. He is also an active reviewer for IEEE transactions on circuits and systems, IEEE transactions on energy conversion, IEEE transactions on sustainable energy, and IEEE transactions on industrial electronics. So, good morning, Arjun. Hope you are hearing me.
Yes, Rajiv, I'm hearing you. Thank you for the wonderful introduction.
Yeah. Good morning. Welcome you on behalf of SIT and on behalf of all the participants participating here. I wholeheartedly welcome you for this webinar. It's yours time. It's your session. Please take up the session, sir. I am handovering to you. Thank you, sir.
Yeah, thank you, Rajiv.
Okay.
It's a pleasure to be here today. I thank the coordinators of this workshop and the HOD for giving me for
Arjun, little bit louder.
Yeah.
Bit louder.
Yes. Thank you. Yeah.
Don't mind. Sorry for the disturbance.
No
Little
problem,
bit louder.
Yeah. You should give me feedback. Otherwise, I'll not know.
Yeah. That's why.
Right. So I take this opportunity to thank the coordinators and the HOD for this opportunity. Right. So without wasting time, we will straight away start with the session. And in case you have any queries, you can put it in the chat window. Or else, Rajiv, you can also let me know if people have any queries, or in case my voice is not audible, if you have any problems, seeing whatever I'm writing it on the pad, you can just let me know then and there, right? Okay. So what I was
Okay, regarding discussions,
yeah.
Arjun, regarding discussions and queries, we
Yeah.
will address at the end of the session. We
Okay.
will give 10 or 15 minutes of time for the participants to address on the what queries. Okay,
Right,
you
right.
calmly carry on. Okay.
Right. Thank
Thank
you.
you. Thank you.
Yeah.
Thank you.
Yeah. So yes. So I'll be using OneNote platform to explain you or to discuss today's topic. Yeah. So today's topic is all about analytical modeling, right? So just a moment. Right. It's all about analytical modeling, right? Right. So the word analytical in electrical engineering is synonymous mathematical. Right. So what I'm basically doing is capturing the working of a converter or working of a system. So system may be a photovoltaic system, or maybe a wind energy conversion system, or maybe a simple converter, right? Mathematically, I'm going to capture that in terms of mathematical equations such that no information about it is lost. And I will use mathematics to visualize the phenomena that are happening. That is what analytical modeling, or someone who does an analytical model does. He understands the working of a converter or working of a circuit using mathematics. Right? It is like a stethoscope for a doctor. Right? So for an engineer, mathematics should be so handy. Right? Without mathematics, you should not be able to deal with the problems occurring in power electronics, power systems, or anything. Right? The thing is, there are so many challenges, advantages and disadvantages. So when you take a concept, the concept has an advantage or a disadvantage, right? So analytical modeling also requires rigorous applications of mathematics. So let's say what mathematics techniques that we use here. So the first technique that I'm using is the knowledge of differential equations. You should be good enough with solving differential equations. Second thing, you should be good with algebra. Third thing, you should be very good with numerical techniques. Right? So these things will help you to understand converters from the point of mathematics. So if you're going for, say, for example, people who are trying for your PhDs, it's very much suggested that you be good with differential equations, algebra, and numerical techniques. Right? So in today's session, we will see how differential equations, linear algebra, numerical techniques will help us solve or visualize power converters. Right? And I'll give you reference books. I usually tell it at the beginning of the session because I forget it at the end. So the reference books are Robert Erickson, author name is Robert Erickson. The name of the book is Fundamentals of Power Electronics. This should be a must-read book for any power electronics engineer. Fundamentals of Power Electronics. This is a must book, right? If you've heard of it, it's good. If you have not heard of it, please go back. It's available. It's available. Soft copy is also available in online. You can go through that, right? And the second book I would suggest is Power Electronics by Professor Ned Mohan. Ned Mohan's book. So these books are the must. If you feel that this is a little too much for you, you can also refer to a Power Electronics Fundamentals by Professor Daniel Hart. Right? These three books should be in your bucket list. Right? So this will train you to look power electronics in a totally different dimension. Right? So most of the things that I would be discussing are either picked up from Robert Erickson, Ned Mohan, Daniel Hart, right? And I've conceptualized it in my own way and presenting it to you, right? And the mode of simulation and to visualize, as I told you, see, these are all equations, right? You need to solve them. You cannot solve them every time by your hand. So you need to use softwares that can do work for you. So that way I will be using MATLAB, right? And most of us, we use Simulink, right? We use Simulink to, to solve these converters, but I will not be using Simulink. I will instead be using M-File. So this is something new, right? What do? We solve something simple in M-File always. Whenever you introduce MATLAB to a student, you just start with M-File and then you take up Simulink, right? But I'm not doing that. Instead, I'll be using M-File. Let's see what strength M-File has and how it can help you in solving problems, right? So this is going to be what I will be using it, right? So what did we do? We understood what is analytical modeling. We saw what techniques of mathematics we use: differential equations, linear algebra, numerical techniques, right? And the reference books are Robert Erickson, Ned Mohan, and Daniel Hart, and I'll be using M-File, right? And the objective is simple, right? We will start from what we know, right? So if you see a ladder, if you see, for example, a stairs like this, a concept is somewhere at an elevated level. Here is what the concept is, and here we are, right? So we should always start from what we know rather than directly jumping from here. That's what I adopt. So what we do is we will start from what we know, how to look into mathematical equations, right? Solving a simple circuits, and then we'll complicate it. And finally, at the end of the day, you will see that yes, you have solved a power electronic circuit mathematically, right? Okay. So let's get started. Rajiv, is my voice audible? Should I increase my? Should I raise my voice?
Audible, sir.
Okay, thank you. Right. So, fine. So, any engineer, an electrical engineer, right, is always familiar.
Yes, sir.
with
It is. Excuse me.
Yeah. Thank you, ma'am. Thank you.
Yeah.
Yeah. Right. So, whenever we say I'm going to analyze, right, the word I use, analyze, right. First word an electrical engineer is going to ask me is, what analysis are you doing? So there are basically two analysis that is taught. We all know this, right? This is called, one is a steady state analysis. The other is transient analysis. Transient analysis, or is also called as dynamic analysis, right? Okay. Now, steady state analysis, they're not functions of time. Right, whatever may be the time, the answer is going to remain, the current or voltage is going to remain same, right? The best example of any steady state waveform is just a DC voltage. It's not going to vary with the time, right? It's not a function of time. The best for a dynamic, yes, it can be a sinusoidal, right? It's going to vary, it's right over time, or maybe exponential, something like this, right? So you basically have two analysis. One is dynamic and transient, right? And you know that the transient or dynamic analysis at the end will die out and then gives rise to steady state. So if someone can do a dynamic analysis, then it's already known that he can do a steady state analysis, right? So let's get started with a most simple circuit, an RL circuit, right? So we will start with something, a very simple circuit. So this, I'm sure everyone already knows, right? This is an RL circuit. So you have voltage, resistance, and an inductance. Okay, say I'm going to, what I will do is I'll just insert a switch here, right? Switch, right? I just copy it. I'll just put it in one place, right? Let it be here. I'll be using it now often then. Okay. Now, when I say an RL circuit, I'm going to say, for example, let's do a transient analysis for RL circuit, right? Why am I doing an RL circuit instead of starting a power electronic circuit is, any power electronic circuit is always consisting of an R and L. And let's take an example of a boost converter. Right. So this is R, C, diode, inductor, as a switch, and inductance. Now I say when a switch is closed, I have a circuit like this, right? I'm only talking about this portion of the circuit. And when the switch is open, I'll get a circuit like this, right? So if you see, these are basically an RL and an LC or an RC circuits, right? So the objective is very simple. Understand the behavior of an RL circuit properly, and I'm going to extend the same principles for power electronics. I'm not going to see power electronics as something different. No, I'm not treating power electronics as a different subject. Power electronics is a wing of electric circuits, right? The moment you realize this, then the way you look at power electronics is going to be totally discussion. I'll give a lot of emphasis on understanding how an inductor, resistor, and a capacitor work. And once you understand that, I'm going to apply the same principle for power electronics. The only difference is that it has a switch, which is same thing. I'm going to understand RL circuits properly, in depth, right? Look it from a different perspective, right? Under different ways, and each of the methods are going to give you a different view of looking into circuit, gives you different information, and I'm going to apply the same thing for any power electronic converter. That is the objective. So let's get started. Right, and once we understand how an RL circuit works mathematically, then I'm going to take help of MATLAB to visualize the response. That is what I'm going to do. Right, so let's get started. This I'm going to delete. Right, okay. So let's say I'm going to do a transient analysis. So when I say I'm going to do transient analysis, the first analysis is very simple, right? How do I start? We all know we start with differential equation. So when I write differential equations, we know V equal to Ri of t plus L into di by dt, right? Okay. So how do I solve this, right? Okay, we have all studied linear differential equations, right? Now let me write it in the standard form. L di by dt plus Ri of t is equal to V. Simple, right? Now this looks like a linear differential equations of the first order, right? So how do I solve this? Simple. I know I of t is e power minus r by l into t, in integration e power minus r by l into t into v by l, I'm sorry, this is plus v by l plus c dt. So this is going to be minus r by l into t e power r by l into t into r by l into v by l plus c. I'm sorry, this is l by r, right? Into l by r. So l and l get cancelled. So what I'm left with is v by r plus c e power minus r by l into t. This is what I'm left. What I did, I just used the solutions method of linear differential equation. What it says, you have I by dt plus q into I is equal to, say, some function or say some r. So you can write it as di by dt is equal to q by p into I is equal to r by p. Equation of this form, you know, I is equal to e power, right? You have something called as an integrating factor, right? E power q by p into dt. So the solution is I is equal to e power minus q by p into t dt into integration of the same factor q by p into dt into r, right? R by p, this factor plus c. So this is what I've got it from the mathematics. I'm just applying it. So using the knowledge of solving linear differential equations, I could get this answer. I of t is equal to v by r plus this. Now let's take a look at what it says, right? It says that, right, I of t has two components, v by r and this, right? So you already know, if you don't know mathematics, if you don't know all these things, all whatever, this entire portion, if you don't know, you can still write this equation. How do I know? How do I write it? You know that any circuit, an RL circuit or any circuit, will have two states. One is a transient state, so a total response plus a steady state response. I know transient response exists, steady state response. For transient responses, a transient response is going to die after some time. So if something is decaying or dying, I'm going to write it as e power minus function, right? E power k into t. It's dying with some rate, right? It has some exponential e, c. This is the transient. And what is the steady state? You know, steady state does, whenever I close the switch at t equal to 0, after some time, d phi by dt, or it's going to, there is no rate of change of, you know, flux here. So what happens is it's going to be a constant voltage. Therefore, inductor gets saturated, and what it effectively sees is just an R circuit like this. You know this. This is a physical process that's happening. So V equal to R, and you know the current that is flowing is V by R. Don't you think they both are same? Yes. So without using the knowledge of mathematics also you can do this. Let's see what is K later. So if you just compare these two, K is nothing but R by L. As simple as this. So you know method 1 how to solve, you know method 2 how to solve. Both of them have advantages. The advantage with method 1 is you don't have to know what is happening inside the circuit. You can just solve it. Now where this comes handy, whenever you have a complicated circuit, when you don't know how the circuit works, you can use this method. And when method 2 works, when you don't know mathematics, you can, if you know the physical process that is happening, you can use this method. Right? I'm going to introduce you to third method. It is more simple than this. We're going to simplify it. I'll just copy it. Right. Paste it. Right. The third method, which is more simpler than this. So I will start from the same differential equation. Writing differential equation is just writing KVL, right? So there is no difference in this, right? So I know that it consists of transient response and steady state response. I will use that only. I of t is consisting of transient plus steady state. Now I know that steady state, right? All the, if you already know, say for example, say the response is like this, right? Okay. You know at steady state, not just the circuit, any circuit at steady state, what happens is there's no change in the output. I is going to remain the same, right? So what is di by dt? Di by dt is going to become 0, right? So I'll just make, the moment I make di by dt 0, right, in the equation, the moment I make this 0, what happens? I is equal to V by R. I can write it that way also. And transient response, you should understand one thing. Transient response is independent of input. Transient response depends only on the value of the components that you have placed in the circuit. It does not depend on the excitation system. No, it does not depend on this. Right? So therefore, I am going to make V0. Right? When I make V0, 0 is equal to R into I of t plus L di by dt. And you know how to solve this using variable separable method, right? Minus Ri of t is equal to L into di by dt, or you know that di by I is equal to minus R by L into dt. If you solve this, you're going to get it as minus R by L into t with some coefficient. No, this is again the same, right? If you just know some basics of integrations, this cannot be even grouped into, you know, actually a solution techniques of differential equation. I'm just, you know, separating the variables and I'm solving it. You don't have information about anything about the system, you can still solve. And this will tell you why in the previous page this K becomes R by L into T. That's because it's coming here. This is because of minus R by L into T. So this is the third method, right? All are giving you the same response, same answers. All will give the same answers. I'm just trying to look things from eagle's point of view. What does an eagle do when it's flying at a very high altitude? It sees things from, you know, at a larger angle, right? It covers squares of kilometers, right? So I'm doing the same thing. Why, when this becomes handy is when you know a power electronic converter, you just have to analyze a power electronic converter without knowing what is actually happening. You cannot do it. There are 2 inductors, 3 inductors, 2, 3 capacitors. You don't know how they work in coordination. That time you can, without knowing the physical phenomenon that is happening, you can still solve them. That's why I'm giving little time for an RL circuit, right? If you know how to analyze an RL circuit or an RC circuit, you will be able to analyze any power converter, right? Now let's say point number 4, fourth method. More simpler. I will again take the same equation, right? I will just write dIL by dt, L dIL by dt is equal to V minus R into I of t. So what is di by dt? Di by dt is 1 by L V minus R into I of t, right? Now I know what is rate of change, right? Rate of change means incremental, right? I of n, right? I can take it as I of n minus 1. The difference dt is t of n minus t of n minus 1 is equal to 1 by L into V minus R into I of n. Sorry, this is going to be n minus 1, right? It's a previous step. Okay. N minus 1. Because this is the present. So this, if I see a graph, say for example, we'll take the same graph, all right? This is Tn minus 1 and this is Tn. Right? This is called as h, or an incremental value. So what I will do is, I will write I of n is, I will send this to the other side. This is going to be h by L V minus R I of n minus 1, right? Plus I of n minus 1, right? So I know the initial condition. These are the initial conditions. It's given, right? I of 0 is something like that. I know initial condition. I can always predict what is going to be the next step. So I know what is the value at this point, right? I know I of t of n minus 1, I of n minus 1. I know what is the incremental I'm supposed to do. Increment is Tn minus Tn minus 1. I know what is the inductance. I know what is the voltage. I know what is the resistance, right? I can always predict. So this does not even require the knowledge of differential equations, right? But what new insight it gives? It gives a new insight that if you know the previous step, I can always predict how the equation moves or how the trajectory moves. And this will help you to solve using computer techniques, or say for example using simulation. What I'm going to do is I'm going to use a for loop, right? For n equal to 1 to some up to, say for example, this level. Then I will write the code inside and then I will write the end. What is going to happen is later I'll use the plot command, plot of, say for example, time versus I. So this is going to give you this response, right? This is the fourth method, right? Now if I extend the same thing, I'm going to extend this. Let's see what more knowledge you'll get out of it, right? What I'm going to do is I of n is equal to h by, you know, this entire thing is what? 1 by L V minus R of I of into t. This entire portion is nothing but f dash, right? Or you can call it as di by dt, right? Yes. So I'm going to call it as di by dt plus I of n minus 1. So what it says is, you take the graph, right? I know some point, say for example this curve, I know one point. I know what is I of n minus 1. I also know what is Tn minus 1. If I just know what is the slope, if I draw a tangent, right? If I know what is the slope at this point, I'll be able to predict what is I of n. You don't even have to know this function. I don't know what is V minus Ri. I just know what is the initial condition. I know di by dt at that point. I can always get what is I of n. So this is fifth method. Sixth method, I can go on giving you like this. Sixth method is very simple. Everyone uses Laplace transform without knowing what it does, right? I'm not covering more of Laplace transforms. Sixth is this. right? Seventh is I'm going to take you into a different domain now. V equal to Ri plus L di by dt, right? Now I'll take all the differentials on one side, the algebraic on the other side. So L di by dt is equal to V minus R into I, and di by dt is 1 by L V minus R into I. And what is I? I is integral 1 by L V minus R into I. If I solve this integral, I'll get. But the problem is to get I, to know I need what is I, right? This is of the previous step. So we all know how to, if I develop it into a form of a control system block, you know how to solve it. So let's do it that way. So what I do is, I will just subtract Ri from V. So this is V. This is Ri. I don't know from where R and I are coming from. Let's see it later. So V minus Ri, right? Now how do I develop this? I'll know what is I coming. I'll multiply with the gain R. So V minus Ri, and I have, for this I have to divide it by L. 1 by L. And what do I get? If I do this, I'll get what is di by dt. This portion is di by dt. Just a moment. I cannot do it here, right? Di by dt. So to get I from di by dt, I have to integrate it. Simple, right? What I get is I, and that I is being fed back. So this is, now it looks similar to your feedback system, right? Plus minus, you have g of s, e of h of s, and this is what you get it as I, right? So this looks same, right? So you can transform that into form of a control system blocks and apply control system techniques. So once I get it into this form, you know how to apply control system techniques, right? To solve it, right? So this is seventh method of doing it. So if you see, all the methods, all are effectively the same. There's no difference between each of them, right? Just a moment. Right. Now you know this. Then when I transform this into a form of control system block, you get the idea of step response. Step response looks like this, right? It sometimes has oscillations, damped, undamped frequencies, all that you know. So if I go back to the last page, now this also looks like step response. Right? What is the final value? Final value should have been V by R. So it's slowly rising to this portion and then going back here. Right? So this can be looked from how many different ways? This can be looked from at least 7 different ways. One is by solving the differential equation as it is. Second thing is having the idea of the circuit phenomenon that is happening, not by looking into mathematics point of view. Third method is, you know, making the differential 0 at one point, making the input 0 at one point, you're getting the answer, right? The fourth method is solving this, just assuming that di by dt is nothing but rate of change of current. So I will be able to predict the next step from the previous step. Then you know, from there we saw graphically what happens. I don't even need this function. I just need the differential rate of change of the previous step to predict what is going to happen in the previous step. Right? Now this is actually y equal to mx plus c. Right? Y equal to mx. X is the h. M is di by dt. You know that this is the previous intercept. So the seventh method of doing this is, the seventh method is that you looking it into a control system problem point of view, right? So when you look, so many methods exist to solve a simple equation or to solve an RL technique, you feel now you're a little secured. Yes, given a differential equation, I know there are methods to solve, right? This can be applied to even second order differential equations. So if you have just an RLC, I just have to, you know, put it into this can be a you know, sinusoidal response, or this could be what you call a DC value. You can still apply the same principle, right? What I would suggest is you just here what happens is you just get second order differential equation, right? And you know there are techniques to solve differential equations of second order, right? You know you have to evaluate the particular integral, You have to evaluate CF. Otherwise, you can break second order differential equation into two first order differential equations and apply all these methods. So all of them will work. Right? Now, what I would suggest is just go back to your workbooks and then solve the same RL circuit using a sinusoidal response V equal to Vm sin omega t. Right? And you should be able to get an answer like this. It is some function k equal to minus r by L into t plus Vm by z sine of omega t minus phi. Right? If you're solving this, that's when you will get to know why there is a phase shift in case of an RL circuit. We always have this, tendency of writing it. So I have a sinusoidal excitation. The response is going to be delayed. You don't know why it is delayed. Most of us, we don't know. If you know, it's good. Most of us, we don't know. But some circuits like this, when you really don't know, see, when you look at a circuit like this, looking at the circuit, you don't know what is causing the phase shift. How is inductor causing a phase shift, right? Inductor works based on the flux principle, but how is that altering the phase shift of the current? If you want to know, mathematics is the best tool for you to analyze. Whatever steps I've told you, I'm going to mail you. I'm going to send the organizers the PDF of this entire workbook. Okay, so you just use these principles and then apply V equal to Vm sin omega t and try getting it. It's a very good exercise because you will know to get into a form wherein phi is introduced. It takes some sort of mathematical manipulations, right? It gives you very good idea about why phase shift is like this and why impedance triangle is like this. Why this is phi, this is r, this is xl, and this is impedance. Why this comes? All these things can be addressed when you're solving this. You can take this as a homework and then solve it for yourself. Once you solve it, you'll get a lot of confidence that yes, I'm able to solve any RL circuit. Right? And maybe later you can extend it to introducing capacitors also. Right? Okay. If you have any doubts regarding whatever I've been, okay, there have been so many. Are there any doubts? You can put it in the chat box.
No doubts, Arjun. You continue.
Okay, thanks.
If anything is there, I will get back to you at the end of the session.
Sure, thanks. Okay.
You don't worry about chat box.
Right.
Continue.
Okay, fine.
Okay, Arjun.
Yeah. Right. So we solved one RL circuit, right? Now we can continue the same for an RC circuit also. The methods are the same. The response you get is according to the circuit that you have implemented. And one point that you have to note when you solve an RL circuit or circuit of which gives you a linear differential equations of first order is they always follow this response unless and until the excitation is constant. Right? They always have this response. That means it is going to have a transient and then die out. Now, this is also applicable for power electronic circuits, which gives you single order differential equations excited by a constant source of voltage V. I'm going to apply the same principles. Let's get started with that. So let's take an example of a boost converter. You can take a buck converter or a boost converter. Anything is fine. Right. So this is an R, this is C, diode, switch, inductor, and voltage. Now what I'm going to do, first step is, I know the switch is going to close and open, right? I will draw the circuits how they were looking, how they look when the switch is closed or open, right? So this is when the switch is closed. I know when the switch is closed, inductor is going to charge, right? Inductor is going to charge. So minus is going to appear on the diode side. So diode is going to be open, right? So this is C and an R. Now when the switch is open, the energy that is stored in the inductor has to discharge. So for the inductor to discharge, this is plus and this is minus. So diode is going to see a positive voltage. Therefore, the diode is going to conduct. So simple as this, right? V, L, C, and R. Now this looks like a different. So these two are two different circuits. Now this is one circuit. Now you basically know, right, that L di by dt. So if I write an equation for this is L di by dt is equal to V, and C dVc by dt, that is current, I'm assuming this direction is going to be minus V by R. This is V in, this is V naught by R. So you know this is the linear differential equations of first order. So obviously it is going to follow this response. Right? This is when the switch is closed. Right? Now, when the switch is open, I will write L di by dt is equal to V minus Vc. This is a linear differential equation of first order. C dVc by dt is equal to IL minus V naught by R. Right? How am I doing? I'm applying KCL at this point. This is IL. IL minus V naught by R is the current that is flowing through the capacitor. Let's not worry about whether it's charging or discharging. That's immaterial. I'm just applying KCL. And L di by dt is this in voltage minus output voltage. First order differential equations of the second order of the, so it's going to follow this response. The only problem, the additional thing that you should consider is that these circuits are interrelated. That means if I'm solving this, I'm going to get that plus C, right? That initial condition, right? That has to be obtained from this circuit. When I'm solving this, the initial conditions have to be obtained from this circuit. Therefore, solving this manually is little difficult. That's why I'm using simulation tool. Because this is going to switch. Now, because this switches, you're going to have an additional, information, that is a small ripple over this. Otherwise, this would behave something like this. This ripple is because that I'm going to switch. Right? And how am I going to switch? I'm going to switch it at a very high frequency, right? Therefore, the ripple frequency is going to be too much. So it's very clear that if you know how to solve a RL circuit or an L circuit or an RC circuit, you will be able to get the responses. That's not a big deal. Only additional thing is that you're going to get an additional ripple on these steady state values. Now, since this ripple, this ripple is going to remain forever, and they are going to repeat at, equal intervals of time. Okay, even these ripples are considered under steady state. So what I'm going to do is whatever happens over this portion, I'm going to consider it as steady state response. Right? So the steady state response will involve the information about the ripple over this value. Why it is called steady state? There are so many students who ask me questions. Sir, when you write inductor current increases, decreases, you all know this, right? It's varying with respect to time, right? But still it's called a steady state response. Why? The reason is that it is going to come. You have to have a bigger view of this. That means there's a transient at this portion. When you look at a single order differential equation, this is the transient portion. Now these switching components are going to appear in the steady state portion of the entire view. That's why it's called steady state. And this is going to repeat periodically after time. Right? Those sinusoidal response, is varying with respect to time. It can be considered as dynamic. What happens is this is going to repeat after a certain amount of time by itself. Therefore, it is steady state. It is steady over the frequency f. It is steady over the switching frequency fs. That is why this response is called steady state response. Right? What did we do? We started from a simple RL circuit, and then we ended up in a power electronic converter, and you saw that power electronic converter was no different from a simple RL or an RC circuit. The only difference is that it is going to have a switching response. Right? In the further section, we will see how this switching components have come. Right? For now, what we will do is let's go back to an RL circuit and see how MATLAB can solve this and how M5 can solve this. Right? So let's go to yes, MATLAB. Right? I will just open and I'll open, yes, test file. Right. So this is not, I'll open something more simpler. I'll open an RL circuit first. Right. Now, can you see? Yes, I think it's visible to most of you. I assume that you already are well versed with the introduction to MATLAB. So you've done that course, so I'll just go. So what I'm going to do is I'm going to use this differential order equation, differential order solving tool of MATLAB to solve this. Right. So to give an introduction to you, right, I will just explain you the code. And before that, let's see where the code runs. Right. So it's taking time. Okay, so the code is run and you've got the answer. First, to verify whether the code is working, right? So you can see that I've solved a differential equation, right? For an RL circuit. Let's go back to the RL circuit. So what is the condition that I gave there? Right. A DC voltage of 10 volts was applied across 5 ohm resistance and it was 10 milli Henry inductance. Okay. So let's go back and write it there. So an RL circuit, 10 volts was applied, 5 ohms inductor, a 5 ohms resistor, and 10 millihenry inductor. So you know the response is going to appear like this. Right? So what is the steady state value? I know from the physics, I know it is 10 by 5 is equal to 2. And how much it takes? It takes a time of the order, you know, tau is equal to L by R, right? 10 milli by 5. So 2 milli plus, it has to take at least 2 milli, more than that, right? So let's go there. Right. So when you see the response, you can see that it's going to settle down at a value of 2 amps and it's going to take certain time, right? That depends on L by R ratio. Right. Now, how do I solve this? If you can solve a simple RL circuit, you can solve any complicated, circuits, right? That's what is the agenda. So I am using something called a symbolic match toolbox, right? So I'll just assume that most of you have not heard of symbolic match toolbox. What a symbolic match toolbox does is it does something very simple. Right. So you know that in MATLAB, the simple code is like this, no? I want to say, for example, plot y equal to sine x. So what I do is I'll give what is the value of x from 0 to 2 pi, and then I'll write the command y equal to sine x, right? And I'm going to get the functions like this, right? So before defining what is y equal to sine x, I have to define what is x, and for every value of x it is going to solve. But I don't want that. I want MATLAB to understand y equal to sine x as it is. That means let the variable be a variable. I'm not going to assign any value to the variable. I want to do an analysis like this. Where that comes into help is, I'll take same RL circuit. I want to know what is the equation of an RL circuit. I want to solve this differential equation. Then I want the answer in this format, right? I equal to V by R into 1 minus e power minus RT by L, something like this, right? I want to see this. I want the MATLAB to solve this equation. I don't want to solve only when I give the values. This I don't want. I want to write it as it is. So that case, I'm using symbolic match toolbox. So the moment I define that these variables, what are the variables? V, R, L, right? V, R, L, right? The moment I know that these, if I tell MATLAB, no, these are going to be my variables, then if I use MATLAB, then it is going to give me answer in terms of V, R, and L. So let me do that. I'll just show you how I did. What I will do now is instead of 10, I will just make it as V, and this is R, and this is L, and I will give an initial condition of 0 current. Okay, then I will not use this. I will just, right, now I will run this. Right, now can you see that here it says that just a moment, I'll just use clear all. I1 of t, yeah, let me run it. Just use one more command called clear, CLC. I've not declared it in terms of y solution. No? Y solve of, okay, this I have to solve. Right. Right. Now when you say it gives a solution, right, v minus v into exponential of minus rt by L. If you just take v by r outside, it was 1 minus e power minus rt by L. Similar. So you don't have to give the values to r and L. It can still tell you what is the what to give. As simple as that. Right. I'll just tell you how could I solve that. So first I have declared the variables. Okay, the variable is, I have given I1 of t. I have not given I of t. Please be very careful with MATLAB. For those of you who are new to it, the symbols like I, pi, right? These matters a lot because inherently pi is 3.142. I is root of -1. You might even overwrite the file. Okay, thereafter your I is going to be whatever you declare. It does not read complex numbers. So I have given, to be on a safer side, it is I1. Then V, L, and R. So V is the voltage, L is the inductance, R is the resistance. And I have to give an initial condition, right? So I have given it as condition I1 of 0 is equal to 0. 2 lines. Then what I'm doing is, then I'm writing the differential equation as it is. So to this, I'll just explain you how did I write it. So how does MATLAB require is, you have V equal to Ri of t plus L di by dt. It wants di by dt on one side and the rest everything on the other side. So it is actually 1 by L into V minus R into I. So this form is what it expects. It wants di by dt on one side, rest everything on the other side. So that way I've written it. That is the differential of I of t. Diff of I1 comma t is di by dt. This is V minus Ri by L. Right? Now this is the equation I've written. Then I'm using solving techniques. So let the variable be y solution of t. Desolve is a command that is used to solve ordinary differential equations. Right? What is the differential equation variable? That is ODE. I've stored it in ODE, comma, what is the initial condition? Simple as that. So there is hardly 1, 2, 3, and 4 lines of code. I will give this, I will send, I will mail this to the coordinator. They can even circulate it to you. I have some codes that is written for simple circuits. You will be able to build more on this, right? So when you just run it, it is going to give you V minus V exponential of minus RT by L, RT by L by R. So it is written actually in this format. I'll just write it here, right? It says I is V by R minus V by R into e power minus RT by L. This is what is written. E is written as an exponential. That's the only thing. So they both are effectively the same, right? So if I'm able to solve an RL circuit, you know how we bridged the gap between an RL circuit and a switched mode circuit, right? So you can as well solve that. You just need some programming skills. That's it, right? Now instead of this, what I'm going to do is I'm going to fill some values for V. Let's say V is 10. I'll go back to the previous. This is 10 and this is 10 millihenry. So 10 millihenry. I'm going to solve and I will plot it. Let me plot, right? So I've just given the values of 10, 5, and 10 millihenry, and then I've used a command called fplot. Fplot the equation from 0 to 0.02. And how did I get 0 to 0.02? That should be greater than your L by R, that you know. Right, now it is solved and let's check the response. Figure. Now can you see? Right, okay, there are 2 figures in that, right? Right, so it has taken some time. So it starts from 0 and goes and settles. Now I'm going to change the initial condition. Let's say initial condition from 0 to 1 amps. Then I'm going to just run it. Now can you see that there are 2 plots? Right, initial condition, the red figure is starting from 1 and it has reached. Since L by R is going to remain the same, it almost reaches the steady state at the same time. So these are the conclusions that you should make. whenever see MATLAB gives you the solutions, just understand. So when the initial condition changes, whether the response time is changed, whether the settling time is changing, no, it does not change, right? Initial condition doesn't mean that it's going to settle at a fast. It's going to settle at the same time only, right? That let's make, instead of inductance as 10 milli, I'm going to make it as 5 milli and run this file. Can you see? Yes, now the settling time or the L/R ratio has changed to half. So if you see, this is like almost half of that. It's going to start at the same time of 1 amps and reach a steady state. So once you write the code, it becomes very easy for you to do an analysis, right? But it's very important that you should also have an idea of, at least a rough idea of how a circuit behaves. Otherwise, you'll not know whether the solution the MATLAB gives or any simulation software gives is right or wrong, right? So this could be one very good exercise. You can try it for an RC circuit as well, right? If you have any doubts regarding this, you can always get back to me. And usually in the workshops, whenever I plot 2-3 figures on the same, people ask question, how did I do that? So there's a command called hold on, right? You can use that. I will also tell you something else. You can also find out how much time it has taken for the equations to solve. That command is also there. So that is called as tick tock, right? What I will do is I will write tick before the equation. I'm going to write it here. Just a moment. Right. This is the equation solver. Tick and tock. Tick tock is basically time, right? Tick and tock. I'll just run this now. Right. Here it is going to tell me the elapsed time to solve this is 0.518614 seconds. So it has taken 0.5 seconds. It's right. So you can also have an idea of the time taken, right? And it has also given you 2 minus exponential of 1000t. You can also get the equations, you can also get the plot, you can also get the time elapsed. There are much more features that are available. All you have to do is go to help, and I think desolve it, right? Yeah, so if you go help and then press deep solve, right, it is going to tell you how desolve is. What are the things that it can also do? It can also solve a higher order differential equations. There are examples given, you can try it. The only thing that you should worry is, how do I write differential equations? So once you have differential equations, it can always be solved. Writing the differential equation is important. That is why we did that exercise, right? Okay, so this is about simple RL circuits, right, using MATLAB. Now DSolve is for solving differential equations, FSolve is for solving algebraic equations. Now what we will do now is slowly we will move from differential equations to algebraic equations, right? So I'll just close this and yeah, just minimize. I'll go to this portion, right? So we were yeah, so one step before where we were, yeah, right? So we saw how to solve an RL circuit and all that, right? Right. So we also saw from RL circuit, we made a transition to switched mode networks. The only problem is with switched mode is it is going to switch after particular amount of time, right? So this is about a boost converter. Let's go to one more converter. That's a buck converter. Let's see how buck converter can be seen. See, the idea is simple. All DC-DC converters are derived from buck and boost, right? Buck and boost. If you're able to solve buck and boost, combination of buck and boost is buck boost. Now the same buck boost converter can be, you know, can from here only fly back forward. All push-pull converters are derived, right? No, the idea is come from an RL circuit or an RC circuit. From RL RC circuit, go back to buck and buck boost converter. Once you know buck boost converter, you can solve flyback. So that will cover entire DC-DC converters family, right? Instead of sitting and solving each of them, solve one of them in such a way that you'll be able to solve all of them. That's the idea, right? Okay. Now, where were we? We were here, right? This portion. We know, I told you why this is called a steady state, right? Now, this is called steady state because it is going to appear in this portion. See, we only talk about this portion. We are not worried how this came like this. This is because of these differential equations. If you are well versed using Simulink, you can try this using Simulink also. You will be able to capture the entire response. I'm not solving using Simulink because I assume that you are already well versed using Simulink. Most of you, Simulink or SimPar systems, you can use that, right? Now what we will now do is, let's work a little bit on this portion. So we know that differential equations has already given you this response. Now this we are not worried about. We were not worried about these days. And now let's see how these appear, right? So let's take a boost converter. Oh, I was telling you how a buck converter is derived, right? Right. I'll tell you that and go to boost. No, boost converter, buck converter, right? Now to understand how buck converter is, let's take an RL circuit. This is an RL circuit, correct? Now I'll add a capacitor here. Why I'm adding a capacitor? I want to make the output voltage not very much over function of time. Let the slope be minimal. I'll add this. Then what I will do is I will add a switch. This is the voltage V. Now you know how to analyze this circuit. This is a simple circuit. You get two first order differential equations or one second order differential equation. This can be obtained. Now let's see what happens here. Now the moment you close the switch, the entire voltage V appears this portion. The moment you open the switch, what will be the voltage here? Let's say 0. I'm not. But there is one problem with the circuit. The problem with the circuit is, you know that inductor current you cannot interrupt, right? There's a big problem with inductor. V is equal to L di by dt. This is the equation governing it, right? Now when the switch is closed, fine, a happy current is flowing through this. When the switch is closed, what happens? This is an open circuit and the current becomes 0. When current becomes 0, say suppose the current is like this, I, and the current becomes 0, it is going to come like this, correct? Now this di by dt is huge, right? Now when di by dt is huge, voltage induced is huge. This might break the inductor. So what I will do, don't want that. So what I'll do is I'll put one more switch. So when this switch is closed, this switch is open. I'm going to operate it like that. So what happens? A happy inductor current flows. So when the switch is open, this switch is closed, so that inductor still have a closed loop for the current to die. Right? If I give this for a long time, inductor current is going to die. Then again, I'm just turning on, I'm turning off. I'm going to get a response like this. Now this effectively is basically giving you a square wave, right? This is voltage V and this is 0. Now the same circuit, I can look at it this way. What it does, at one point the voltage is high, at one point the voltage is 0, which means it is short, right? So this is basically a simple LC circuit. Instead of feeding a wave like this, I'm going to feed a square wave like this. What you define this as totally a different converter called a buck converter in terms of circuit analysis would be a simple LC circuit with just a square wave excited. If you can solve this, yes. Now what I'm going to do is, see, you know that when the square wave is at the highest portion, inductor current is going to rise. When square wave is at lower portion, inductor current is going to decay. If you give a lot of time, it is going to be 0. Again, it is going to rise, it is going to fall. Now, this is called as the time period, right? This is the time period. So let's put it this way. Okay. So this is the on state. This is the off state. What our inductor current looks like, right? So you can effectively see that you don't need a special, emphasis to solve power electronic circuits. It's just an extension of electric circuits. Boost converter is also the same. If you know buck and boost, buck boost is the same. Sepik converter is the same. Flyback and forward converters are the same. Essentially, all families of DC-DC converters are the same. Right? Now let's go. So this is how we solve buck and boost, just with the knowledge of circuit analysis. Now let's go a little deeper into converters and see how these ripples are appearing. Right? Okay. So we saw how a buck and boost converter works. We'll go a little deeper into a boost converter. See, all these things I'm discussing now is already what you know. I'm just giving you a new dimension. That's it. Switch, capacitor, and a resistor. Right? Now you know how both of them work. Right? Now let's again take the same. Let's go back to the case when the switch is closed. Okay. So when the switch is closed, I'm not worried about capacitor. Whatever analysis I make for inductor, I'm sure you'll be able to look at for the capacitor. So this is the L, this is V. Now you know that when the inductor, now this is the portion when the inductor is charging, right? So when the inductor is charging with respect to time, I'm not capturing this response now. I've already told you how this comes and how this comes. I'm only looking into this portion. So you know that there is already a base. This is already an average current that is flowing because of the differential equations. Now I'm only talking about the switching, right? I'll plot both the response in just one plot, and this is when the switch is off. This is V naught. This is L and V. I'm not putting capacitor. No. When the switch is on, when the switch is on, the inductor has to charge. Now, when the inductor has to charge, how do I write the equation? V L di by dt. And what is di? Di is the rate of, is the incremental current, and this is delta t. This is V equal to L. And now L is V into delta t by delta L. I'm sorry, delta I, right? Yeah. Delta I. Now, this is only when the switch is on, right? So if I give a pulse like this is on time. Usually it's denoted as dts, and this is as 1 minus dts. Correct? So V into, during this portion it is going to charge, right, by L. So you know that V is positive, D is positive, TS is positive, L is positive. Therefore, the slope has to be an incremental slope. Why am I starting from this portion is because I have to maintain the average, right? That is from this response. Now, the moment when the switch is off, you know, delta I is now rightly from this equation, I can write V minus V naught. Wherever there is voltage, I'm just writing V minus V naught. Delta T is 1 minus D into TS by L. So this is positive, this is positive, this is positive, but V minus V naught is not positive, it is negative, because V naught is greater than V. So therefore, the slope is negative. So this continues. Now, you have to design an inductor such that these portions are effectively the same. Right? You have to design an inductor, these portions are, that means you should not allow the inductor to saturate. If the inductor saturates, or if these portions are not same, what happens is, it is like this, then, okay, I'll just plot it here. This is time and this is the voltage. So suppose, say for example, okay, this is like this, right? So before it reaches this actual portion, it is going to again rise. It rises. That means these points should all, be the same effectively. If that does not happen, what happens is your current rises and finally your inductor saturates. Right? That should not happen. Therefore, you have to design an inductor such that it is going to discharge to the same level as it was before. That is called designing an inductor. Right? So if I have to do that, then what I should do is, I should make sure, if that should not happen, go back to the equation, I should make sure that over the entire switching time Ts, the rate of change of inductor should be 0. That means L into di by dt is 0. What it means is, if I have an inductor like this, right, this portion should be same as this portion should be same as this portion. Now this is called as one cycle, right? This is called as one value of Ts. Now over the entire cycle, the net change in inductor current should remain 0. Therefore di by dt is 0. This di by dt is different from di by dt I was talking here. This, the older di by dt is capturing this portion. There di by dt exists. Right now I'm talking about di by dt here. Though there is a change, incremental change, but over the entire cycle, that is from this portion to this portion over Ts, the net change, net inductor change is supposed to be 0. You have to design your inductor in such a way that this happens. So if I have to do that, right, then I'm going to, that means the net change in the inductor current, that is delta I, has to be 0. What's the net change? This is positive slope, this is negative slope, right? And you know that positive slope is V by L into dTs plus V minus V naught into 1 minus dTs by L equal to 0, which is why you're going to give V by 1 minus D is equal to V naught. Otherwise, this will never hold good. What I mean to say is, if you are making sure that this equation works, then yes, your inductor is not going to saturate. That is what you should understand when you write V naught is V by 1 minus D. How did this come? It came from this principle. Volt second balance is what you call. Most of the time we don't know what is volt second. It means that I'm going to maintain average voltage across inductor 0. And why should you maintain average voltage across inductor 0? Otherwise, if you don't maintain average voltage 0, your inductor is going to saturate. You know already inductance saturates when you provide a DC voltage. This is basically a DC voltage only what you're giving. But how you're giving this, you are giving it in terms of switch. Therefore, making sure that the inductor does not saturate. Right? This question usually students ask me whenever we have explained the concepts of switch mode power converters. Right now, this is therefore a positive slope, negative. Same thing you can apply for capacitors also. You'll get the same thing. Therefore, that is why, because since these points are the same, right, it appears that when you're sitting at this portion, right, when you're looking at it exactly at Ts amount of time, you see that the inductor current has not changed at all. It's like as if you are wherever you are. It's going to appear, it's going to repeat itself after every Ts amount of time. That is why it's called a steady state. Correct? But the steady state response, whatever you study in textbook, has some problems, right? What's the time? Yeah, 12:10, right? Okay. So this steady state and this equation has some problems and has some limitations. Let's look into what is that. V naught is V by 1 minus D, right? Now, one thing is it makes sure that your voltage across inductor is 0, average voltage across inductor is 0, which means that your inductor does not saturate, right? So your converter works. Now let's see what is the problem with this saturate, right? Now let's see there is some problem with this. Let's see what is the validity of this equation. Okay, same boost converter. Okay, right. This is V in and this is V naught. Now, say I'm going to see what does it say? It says that you give some duty cycle. I'm going to tell you what is the voltage. If the duty cycle is 0.5, the voltage is double. If the duty cycle keeps on increasing, the voltage increases, making it as a boost converter. Now, if I plot this versus duty cycle, when duty cycle becomes very high, 1 minus d is small and this factor, multiplication factor, increases by a great amount. So you basically get something like this, right? So therefore, at say duty cycle equal to 1, you get an infinite voltage. But whether generating an infinite voltage is possible, practically talking, it's not, right? So what happens? Let's see what happens when I make duty cycle equal to 1. When I make duty cycle equal to 1, my circuit is just this. I've isolated two parts. What happens? Inductor keeps charging, inductor saturates, right? Inductor saturates. Now capacitor keeps discharging. Capacitor discharges, it does not have source of charge because duty cycle is 1. So when the capacitor discharges, finally what happens? Output voltage decays. But according to the equation, output voltage should be infinite. So that means there is one problem with the equation. It's not giving you total response, right? This is point number one. Point number two, what I will do is, say for example, this is connected to some motor load, right? We are doing an experimentation. I am going to control the motor, DC motor. What I will do is I have a voltage of, say for example, 300 volts, right? No, this is a boost converter, right? I have some, say, 100 volts or 200 volts, and you want some 230 volts or 300 volts for the motor to run. I'm going to decide what is the duty cycle based on what I want. I want 300, 100 volts, 0.6, something like that. Now what I will do is, usually what happens is I will have some switches connections here. Okay, I usually do that, right? You keep some switches here, right? You just don't know what is happening. You don't have no insights of the converter properly. I say, let's stop the motor. This is already working like this. I'll say, let's stop the motor. So what you will do is, one of the students, you just remove this contactor. So what happens? This becomes totally isolated. Now, because this becomes totally isolated, what happens? Let's see. When the switch is closed, now remember, we are working at a range of tens of kilohertz. Tens of kilohertz is 10 to the power minus 4 seconds. That means there are 10,000 cycles in 1 second, 10,000 ons and off that are happening in 1 second. You only know how to measure seconds. We don't know how to measure this, how small these are. We don't have idea about it, right? Our physical sense does not calculate this. Now, in just 1 second, 10,000 switching operations happen. Keep this in mind. Now, let's say switch is closed. I've removed this and the switch operates, right, with some duty cycle. Inductor stores the charge. The moment you open this, what happens is, now when this stores the charge, you know that the circuits are totally isolated. Capacitor has to give the power to the load, but there is no load connected. Therefore, what happens is capacitor voltage is not dying. It's going to remain constant. Now, when switches open, inductor has to give the power to the capacitor. That's how a boost converter works. See, I'm assuming that you already have a basic idea of boost converters, so I'm going a little fast. So when inductor is discharging, it gives to the capacitor. So what happens? Capacitor voltage rises. I'm just using I equal to C dVc by dt, and V is equal to 1 by C integration of I dt. Right? Now, whenever there is a current input from the inductor, capacitor voltage is going to rise. It's basically an integration, you see. Right? Then what happens? Whenever the switch is again closed, the capacitor cannot discharge because there is no load connected. So capacitor voltage rises, and you imagine in 1 second, 10,000 such operations happen. So the moment you open your capacitor, if the voltage exceeds greater than the capacitor voltage, then what happens is your capacitor is going to blast. But you don't know why. So you should have a physical insight of this level. But when you only know is from the textbooks, V0 is 1 by SP. Therefore, there is one more limitation of it does not tell you that it's a function of load. This has to be there. Suppose, for example, by mistake you short it. When you short, what happens? Capacitor totally, gets shorts. The voltage across the short part is 0, but it does not say that, right? So you see that though you derive equations, right, you should be able to understand what information the equation gives, what information the equation doesn't give, right? Now these things the equation doesn't address. Therefore, you need to go a little detailed modeling of it. Let's see how can we do that. So 3 things it is supposed to tell you, main 3 things, right? One thing is what happens when duty cycle equal to 1? What happens when R equal to infinity? What happens when R is 0? This it is supposed to tell, right? L, switch, diode, capacitor, and resistor, right? So we are going to wind it up at the right time. Okay. Now what I'm going to do is I'm going to consider a practical converter. What happens? A practical converter will have a small ESR. It has a small switch resistance and a voltage drop across the diode and a small resistance. It has a small ESR, right? So let me name it as RL, RSW, This we will name it as V capital D, R capital D, and this is RC. So the voltage given is V in, output is V naught. Even in practical converter, one principle should always hold good, that the average voltage across the inductor should be 0. Right? So let's see what is the average voltage. So let's take the circuit when the switch is closed. When the switch is closed, the circuit appears like this. See, whatever I'm doing for inductor holds good for capacitor. I'm repeating it. I'm not worried about that part. L, RL, and RSW. This is the input voltage. Now, what is going to be L di by dt? L di by dt is V in minus IL into RL plus IL into RSW. So di by dt is V in minus IL RL plus RSW by L. So when the switch is open, you have RL, L, diode drop VD, diode resistance RD, and you have V naught. Right? Now L di by dt is RL into IL, right, plus VD, I'm sorry, minus, right? 1 second, L di by voltage across inductance is main voltage minus, sorry, I made a mistake. It is V in minus RL into IL minus VD minus RD into IL minus V naught. So therefore di by dt is going to be L. I just have to add it and make it 0, right? So if I add it and make it 0, V in, right, so let's put it this way. I'll simplify it even. I'll just copy these equations first. To the next page. Equation 1. And equation 2. Right. Now, therefore, delta I is V in minus IL into RL plus RSW into D by Fs into L. Here it is V in minus RLIL minus ILRD minus VD minus V naught by L whole multiply by 1 minus D into Fs. Ts is 1 by Fs. Now sum I have to make it 0, right? So this is going to be V in. Now you see I'm going to add both of them. I'm not explaining every step. D and 1 minus D together is 1, right? So I'm going to write V in minus IL into RL plus RSW will be multiplied by D. Plus and minus is minus RL. IL is 1 minus D minus ILRD into 1 minus D minus VD into 1 minus D minus V naught into 1 minus D, right, should be equal to 0, right? Now V in minus, now RL is coming at both the times, so it is minus IL into RL minus RSWD IL, right? So this is done, this is done. So these are all simple. IL into RD into 1 minus D minus VD into 1 minus D minus V naught into 1 minus D is equal to 0. right? Now I have now IL. I don't want. What I want is I want an equation V naught, which is a function of V in, which is a function of duty cycle, function of R. R means including the load resistance and all these resistances, right? So now when you know that, see, you know this, yeah, switch, diode, capacitor, right? You know that capacitor does not take an average current through the capacitor is 0. Therefore, diode current average is equal to load current average, right? So this is average load current flows through the diode. Now you know this also, right? Only when the switch is closed, only when the switch is open, the currents here are saved. So therefore, only a portion of inductor current flows through the diode. Therefore, and that's when only when the switch is open, right? So it is IL 1 minus D times of IL is going to be I naught, and I know 1 minus D is V naught by R. I'm sorry, this is, yeah, I'm just eliminating the steps because I know the answer, right? For IL is V naught by R into 1 minus D. Now I've expressed IL in terms of V naught, R and D. So if I do the calculation, I will get V naught is, you can do it at your, I'll give you the PDF, you can do it later. V in minus 1 minus D into VD. VD is small VD or capital VD, I'll use capital VD. That is a diode drop, right? Into 1 minus D into R divided by, this is RL plus RSW into D plus RD into 1 minus D, right? Plus R into 1 minus D. You get something like this, right? So now you know that it's a function of resistance, right? V naught is a function of resistance. The moment I make, say, duty cycle equal to 1, right? So the moment I make duty cycle equal to 1, this portion is 0, this portion is 0, right? 1 minus 1 is 0. When 1 minus 1 is 0, then I don't have to bother what is happening here. So the moment I make duty cycle equal to 1, I want V naught as 0, right? That's what is happening. So this becomes 0, this becomes 0, the numerator portion becomes 0. So V naught is equal to 0. And the moment I make R is equal to infinity, the second clause. First clause is what happens when D equal to 1. Second clause is what happens when R equal to infinity. When R equal to infinity, you can see that infinity appears in the numerator itself. And this is going to be infinity. So this is going to be infinity by infinity, right? Which is a indeterminate form, which is an unstable form. That is what happens. Your boost converter becomes unstable and it's going to blast. And what happens when R equal to 0? When R equal to 0, you know this portion itself becomes 0. When this is 0, V naught is 0. So all these things are addressed. So you, whenever you derive an equation, you should also know the limitation of an equation, right? Now, if you are able to, if you can devise this equation, it's very good. But the problem with this equation is, you know, say suppose I want to, you know, calculate, say the output voltage is 30 volts, my input voltage is 15 volts. Say, let's say what can be, how can be D. If I'm using a smaller and simpler approach, V naught is equal to V by 1 minus D, it's very simple, right? I know how to calculate. D is equal to 1 minus V by V naught. I'll be able to tell 15 volts, 30 volts is 0.5. That is not the case here. How will you get D on one side and, you know, calculate what is D equal to? D I cannot put it. So these functions are basically implicit functions. These are implicit functions. Now this requires numerical techniques to solve. Now this is where role of simulation tools come. Here this is very simple. I'm just talking about design. I'm going to give you a design. V naught is 30 volts, V in is 15 volts, R is equal to 100 ohms, right? Duty, say switching frequency is 10 kilohertz, right? Assume that it's in continuous conduction mode. That's what you usually get it in books to solve, right? So you directly solve it by hand. But if you want a more detailed model like this, now this becomes complicated. This is called as a loss model for DC-DC converter. This can be applied for even DC to AC converters also. Right? So let's go to MATLAB and see how you can design a boost converter considering the loss model and lossless model, how the difference and where the difference is. Right? I will just go back to the MATLAB. Right. So this is done, right? Right. Let's go and open some boost, ideal boost. Right. Now I have taken a case where Vin is 15 volts. I'm going to tell you the volt specifications. Vin 15 volts, RS is 50 ohms, FS is 25 kilohertz, duty cycle is 0.6. I want to calculate V0. So this is a ulta, this is not a design. This is an ulta case. So I know V0 is Vin by 1 minus D. I also know that if you know what is L minimum, you can calculate what is L. You also know how to calculate IL max and IL min. All that, it's normal, pretty normal for a master's or a BTech students to do. So I've just put it in the form of an M file. So what I do is I'll just put the specifications, and I'll write the equations, and just I'll run this file. Simple. Now you can see that it has solved, and it says if you have 30 volts, if you want 15 volts, and if you have a duty cycle of 0.6, it gives you 37.5 volts. The ripple in output voltage is 0.37 volts. L minimum is 96 microhenry. So I'm going to give a margin of 1.25 times. So I need to keep 120 microhenries. The average inductor current is 1.8 amps. The ripple in inductor current is 3 amps. Maximum inductor current that flows is 3.37 amps. Minimum is 0.37. So why do I need a maximum inductor current? Is if you're designing a PCB, you want to know the track size. So that will help. And the capacitor requirement is 48 microfarads. This example is taken from what you call Daniel Hart, right? You can refer to that. The idea is this. See, you know how to design for a given specifications. The idea is how MATLAB can be used to create design files. Now all you're supposed to do is just vary this, right? You just have to vary V0. So what you can do is you can create a repository for all the power electronic converters, buck boost, buck boost. So the moment you just input the values, you can get the responses. You can make it as a part of your lab, this one, or make it as a part of your theory course, right? So what happens is if you do this, you will be able to work on advanced converters easily instead of hand calculations. See, hand calculations are important when you start understanding the circuit. Once you are equipped with understanding the circuit, you can always write design files like this. Keep M files with you, make a repository, right? If you are well versed using Scilab, or if you want to promote open source software, what you can do is you can make files in open source like Scilab and mail it to the French consortium. They are going to the Scilab people maintained by French consortium. So you can also develop, you can also help in building open source files, right? So you just have this file, and then the moment you input the values, it is going to give you the response. This is a simple file. Now I'll just slowly complicate things. Okay, right now the thing is, this is about design. Right now I want to understand when my input voltage is varying, right, how my output voltage, how my what you call IL max, average current, is going to vary. So for that, I have taken a case where output voltage is 30 volts. I want a fixed output voltage of 30 volts. I want my input is going to vary from 12 to 20. Right, my resistance is 50 ohms, switching frequency is 25 kilohertz. I'm just taking the same example, looking at it from a different perspective. Right now, what should be L to be maintained? What should be the average inductor current to maintain 30 volts irrespective of varying your input voltage? So if you look from the point of view of a control system, this is basically what I've done is this. Another page, right? So a converter, I want to maintain an output voltage of 30 volts, and my input voltage is varying from 12 to 20 volts, right? So you know this, right? V in, you give it to a PI controller, and that is going to tell you what is the duty cycle, right? This is given to, you know, what the plant boost converter, and that will generate what is the, I'm sorry, this is V naught, right? V naught, that will give you V naught. The same thing I've done in M file. It's like a closed loop operation in M file. See how easy it is. If I have to maintain 30 volts for a varying input voltage, V in is here, V in is varying. I have to maintain 30 volts at all the points. So calculate what is the duty cycle. Your API controller should do it, right? No, when you, okay. So if you're able to do this, what happens? What is the implication on the maximum inductor current that flows? What is the implication on the average inductor current? So this is very important, because if you rate your PCB for 3 amps and you see that the current is not 3, maybe for a different, you know, input voltage it goes up to 4 amps, then it's difficult, right? So you have to do all these analysis. So for that, M file can be of major help, right? I go to editor, I'll just run it. Now you can see that it just generated 3 plots. When the input voltage is varying from 12 to 20 volts, my duty cycle requirement is coming down from 0.6 to 0.3. And my second is, I think it is about IL max. Possible is 2.7 amps. So when you know that in a circuit, that maximum, you know, the range of input voltages, every time you don't have to calculate what is the maximum inductor current. You just feed it to a, you feed it to an M file like this, and it will give you. So it's about 2.7 amps. So you know the worst possible case is 2.75 amps, 7 amps. So design your PCB for that, right? Similar is this. So you do these analysis whenever you want to develop a product, or maybe you want to develop an experimental prototype, right? And these simulations will help you in that way, right? Now what I will do is, now you can vary your input voltage from maybe 12 to 20 volt, or 12 to 15 volt, or 12 to 25 volts. It is going to give you the answers, right? Now let's take an example of a non-ideal converter, right? Now non-ideal converter, there is one problem. Let's first address that here. You know that a non-ideal converter, V naught, was a function of duty cycle, input voltage, load resistance, and all other parameters. Now the problem is, you cannot remove D from here, and I can write D is a function of V naught, V in, and R. I cannot do that, because the equation, as you see, as you saw, this is very complicated. Now what I will do is, like the way you used D solve, I'm going to use something called F solve. F solve basically solves a equation of this order, something like this, which cannot be solved using hand calculations easily. So you know how to solve them using calculator, right? Similar is this, right? So let's take an example. The approach is this. I will take an example of some simple x cube minus 27 equal to 0, and let me make MATLAB calculate it as 3. If I'm able to do this, then what I will do is, I'll remove this equation and put this equation and solve. That's the idea, right? So let's see how that can be done. So instead of directly jumping into boost converter, I will directly take this. Right, I'll go to open. Let's open these 2 files. Right, I'll just remove these 2, right? Now, what I've basically done is, I have solved an equation x cube minus 27. Now, there is a protocol that you have to follow. There's a syntax, right, for every software. So what I'm doing is, I'm going to define a function file. A function file. There are 2 files. One is a function file and the file where you solve it. The function file has to be, it can name a function and an end is what is going to come here. So you know, f is a function. I'm going to give a name for this function called test of x, and inside I'm going to write what is the equation that I want to solve. X cube minus 27 equal to 0. Put everything to the left side and equal it to 0 and write the answer. And I'm going to call the function file here. Forget about what is in the green that I have commented. Only one line. I want to solve for x using something called fsolve. That was dsolve, and this is fsolve. I'm going to share these files. You can see it later. Use help to understand what I've written. Fsolve which file? Fsolve test file. The test file is this. That's why I've given the name as test.m, test file, and give some initial condition as 14. You know x cube minus 27 will converge at 3, but I don't know that, right? I've given 14. So let me run this file. So it has already run, and you can see that it says equation solved. It's happy. X is equal to 3. Now what I want the whole and soul thing is, I will replace x cube minus 27 by the equation that I've put. Simple. There are lots of additional features that we will see later, but let's run that file first. Ideal boost, non-ideal converter, non-ideal boost, right? Let's open this if I missed. Non-ideal boost.m. Right. Let's run this file. So what is the variable used? dn, right? Okay. So I'll just type dn. Right. So it's working. So let's see what happens. So you know that if I have to maintain the 30 volts, right, from 12 volts for the same specifications, 50 ohms and 25 switching frequency, ideal converter says maintain a duty cycle of 0.6. But a non-ideal model says, no, don't do that. You maintain a duty cycle of 0.66. Right? That means in practical, if you give an input voltage of 12 volts and expect 30 volts for a duty cycle of 0.6, it will not. It will give you a lesser duty cycle. It will give you a lesser voltage. Instead, you have to give 0.66. So you have to increment bit by 0.06. Why? Because it is going to cater to the losses also. There are going to be I square R losses. You know, we have considered years of inductance, years of capacitance, all that, right? So due to this, the voltage is 0.66. So you can actually have an understanding of the importance of studying lossy models, right? So what I've basically done is output voltage of 30 volts, V of 12 volts, R is 50, F is 25 kilohertz. And I have written the equation, same function file. I have written the equation. I've just put this equation here. Simple, nothing more than that. Right? These are the parameters V in, VD, DL, and RSW. And the same thing is solved. And here, what I've done, I've used a trick. I know from the loss model what is the equation, what is the answer. Lossless model, the answer should be near 0.6, right? So if the answer has to be near 0.6, then I'm giving initial condition as 0.6. So it is going to be near 0.6. So lossless model will give you an initial condition for a lossy model. As simple as that. So you can vary RL and check, right? Now the moment I make it, instead of say 30 volts, I'll make say 35 volts, and I'm going to run this. So the moment I make it, right, it says that the equation is solved, right? So I'll just type the duty cycle. Duty cycle instead of 0.66 is 0.72. Right? Once you have this, then rest is going to be simple. You just have to, extend the file. Simple, right? So let's say I'm going to vary converter. Okay. I will just show you these two files. I'll just remove all the other files because that will complicate. Right. So what I've basically done is, if you go to the lossy model, one thing is very sure, right? So the difference is that the lossless model gives the voltage curve like this, V naught versus D, right? That means a duty cycle equal to 1, it is going to reach infinity. But what does a lossy model tells? The actual model, it says it's not like that. A duty cycle equal to 1, the output voltage is 0. So this is going to be the curve. Let's check how it happens here, right? So the next program is to plot that. Can you see? Yes. Now if you see that, there's always, can you see that the blue line is for the lossless model, red line is for the lossy. For a given duty cycle of say 0.25, practical converter will not give you as much voltage as a ideal converter gives, right? This is point one. And very, very high. This affinity, almost it is reaching 250, 300 volts. Converter will not do that. It is going to make your output voltage 0. So if I just plot it, say for example, with respect to say 0.97, right? Then you can see just from 0.95 to 0.97, output voltage from 200 has increased to 400 volts. But the output voltage is coming down to 0. It's hitting the 0 line here at the almost duty cycle equal to 1. So this information you will miss if you're using a lossless model. And I'll tell you where students make mistakes. Students are, most of the time we also make mistakes when we don't have any idea. Okay, say for example, in photovoltaic systems, you want to maintain a DC voltage of say photovoltaics or some system, 400 volts. You have just 100 volts here, right? You have to convert a boost, you have to connect a boost converter. You make this mistake. Okay, I know I have to boost. Duty cycle is 1 minus 100 by 400. 1 by 400 is 0.25. It's greater than 0.75. Minimum is 400. So if you make it 500, this is going to be greater than 0.8. Now you come to this. Let's see whether that is happening. Now you see the moment you make 0.8 or greater than 0.8, your output voltage will start declining here. Your controller, I'm talking about implementation, your controller will not be able to maintain because your output voltage is more. When your duty cycle is more. When your duty cycle is more, what happens? You're giving 0.8 or say 0.85 times of the time for the inductor to charge, and you have only 0.15 fraction of the time for the inductor to discharge. It cannot push the entire energy to the capacitor, right? So what happens? Like period and period wise, your capacitor voltage is going to die. That's what practically happens. That you should be able to capture using equations. Only then you will understand what is happening. So therefore, always for a boost converter, on a thumb rule, it is taken that above 0.85 or above 0.8, 0.9, you will not make the converter work. That in a microcontroller, whenever we do it in the lab, what we do is the first thing, right? So whenever we implement this, we put one saturator here, and you make sure it is from 0 to 0.8. We will not allow the boost converter to operate beyond 0.8. The reason is this, right? You have a switch, diode, right? And you have the rest. So when the duty cycle is greater than 0.8, the on time is more and off time is very less. So when the on time is more, the inductor charges, and the entire energy that the inductor, half Li square, right, has to be put back to the capacitor during just 0.15 time. 0.85 is the on time, 0.5 is one time. When your switching frequency is more and more and more, you see what is the, what implication? 0.15 times that switching frequency, 1 by Fs, is going to be the time the inductor has to push the entire energy to the capacitor. Just think whether that happens. If that doesn't happen, what happens is the capacitor keeps on discharging. And that's why, what happens, you'll not be able to maintain that voltage. This is the reason why this is coming down here. Because the inductor is not giving energy to the capacitor, all the energy, it will have a lot of impact on the inductor also. Because if it does not give out the energy every period, it builds here and the inductor saturates. Right? Now this information you can obtain by writing an M file like this. You can vary your input voltage, you can vary your resistance, you can vary switching frequency, you can vary the range of duty cycle, you can vary the non-idealities and capture the details. Right? So there is one last what you call file, variation in VM, right? There's one more file, variation in, okay. I'll just close this. Yeah, this is variation in input voltage. Now what I have done here is, right, I've just plotted, let me run this file. This, I'll just keep it here, ideal boost, right? Not ideal boost, I'll run one more file, boost, right? Just run this. I will also run this. Yeah. Now, if you see that, what I've basically done is the same input specifications, right? Clear. V0 is 30 volts, input is 12 to 20 volts. 1 second. And resistance is 50 ohms, 25 hertz. I have derived a lossless model, right? I will run the lossless model now. Okay. Now this is the result from a lossless model that we saw. Duty cycle, maximum inductor current, and average inductor voltage. Now this is from a lossy model. Now this what I've did is from the lossy model. I will run this also. Can you see here? Yes. Now if you see that the orange one is from the lossy model, that is from non-ideal it is. This is from the ideal model. So you can see that a same design done using a lossless and a lossy model, there is a difference. Why? Because the duty cycle required to maintain, say for example, I have a voltage of 14 volts. I want to maintain 30 volts as input. Then the duty cycle requirement is little less than 0.6. However, it is greater than 0.6. Now, due to that, what happens? The current is close to 3 amps. Here, the current is 2.5 amps. So there's a lossy and lossless model. Even the steady state values are different. It's not just that it is going to give you an additional information, but it says that you're missing something when you don't consider the non-idealities. That means the non-idealities are going to contribute to most of the parameters. Duty cycle, inductor currents. You can also see, you can also plot the capacitor voltage, not capacitor voltage, the losses in the capacitor you can see that's going to contribute. This is about steady state. Stability wise also, you will have a lots of differences when you consider a lossy model, right? So this is just for a, what's the time? Right, 12:50, right? Yeah. So this is just for a boost converter. Same thing you can derive for a buck or a buck boost, right? Now, if you have, say for example, a photovoltaic system, you know how a photovoltaic system is actually derived, right? So basically, it is a current source. You have a diode. You have a resistance, series resistance. You also have a shunt resistance, right? So once you write equivalent circuit, you can write an equation for IPV, right? So this equation of IPV, along with whatever equations that we derived, V0 equation in the previous, you can solve both of them using fsolve, right? And you can see when a boost converter is connected to that, how the PV is going to behave, where the operating point is, right? Operating point is here. This is a power. This is the current. Whether operating point is here, operating point is here. That depends on the V by R ratio, V by I ratio, right? How the entire boost converter, right? How the boost converter is seen by the PV. If you are sitting on the terminals of PV, this can be viewed as one resistance. It can be later shown that it is a function of duty cycle. That's anyway a big story. So based on what this resistance is, your converter is going to operate. All these analysis you can make just by solving using fsolve. All you have to do is write equation for PV, which you can get it from papers and books. You already know how to write equations for boost. Now you estimate what are the unknown variables. Suppose there are 4 unknown variables. Derive 4 equations. 4 equations, 4 unknown variables. Solve it using fsolve. You will be able to get. So these can be given as assignments for students. Right? First, you create a repository for all the converters. If you are having advanced power electronic course, whenever you study a buck or a boost converter, you ask a student, or if you are a student yourself, keep a file for all the converters. Then slowly, look into papers and then study photovoltaics, how photovoltaics equations are derived, club with these 2 files, and you have PV with a boost converter. Next, you can do similarly for an inverter, right? Similarly, connect it to some motor drive. You can also do it for a wind system. See, any system which can be captured in using mathematical expressions or equations, you can always write such files and make analysis. But when you write an equation, make sure that you write them properly. Make sure your units are correct, right? Solve them properly. And whenever you come up to a solution, you analyze and understand why the solution is this way. Right? This should be a good kickstart for you to start your MTech projects as well as your research. Right? If you have any doubts, I think this is more than sufficient for 2 hours. Actually, this is a material which we usually do for a course. Right? We make student do every program, and then we provide hands-on. But since the time is just 2 hours, I thought this should be enough, right? So what we did is we started from a simple RL circuits, and we came back to transient and steady state of converters. This is how we bridge the gap, right? I'm done, I think. Rajiv, you can take over.
So thank you, sir. It's a very nice session.
Thank you so much.
If you have any doubts,
Any
queries
doubts?
or interactions, if you want to
Yes.
do with the speaker, you can contact now. You can unmute yourself and you can ask, because I can't able to find any doubts or queries in the chat box. I think who has talked in between, it was a good session. Someone else have talked. No, do you have any queries, or if you want to make any interactions with our speaker, you can go. You are welcome. Okay, you can unmute yourself and you can ask.
So my email
sir,
ID and phone number. Yeah, please tell me.
Okay. Sir, is it okay for me?
Yeah, please go ahead. Yes.
It
good
is very
morning.
nice session, because whenever we build the buck or boost converter, we don't think about the designing of inductor.
Right.
And the current passing through and inductor saturation. And
Right.
this session is very nice because of we are dealing with only simulating, but by using M file, it is very easy to solve these equations by using the F solver and D solver.
Yes, sir. That's why we thought I would do it this way. Yeah, correct.
For practicing, is it possible to give the material?
Yes, sir. What I will do is now I will make a zip of all these files. I will mail it to Rajiv. Rajiv should be able to send it across the entire group. I will give this to you.
Okay, sir. And is it possible to for the multi-level boost converter or any type of flyback converters, multi-phase flyback converter in this way?
Yes. Anything is possible. We have actually built much complicated converters. Actually, I have built a multi-level inverter up to, say, I don't know, I think up to 32 levels or 33 levels, right?
Okay.
See, these converters are not existing in real time. 33 level, 34 level converters are just academic purpose and for you to conceptualize. But yes, can be easily built. Probably if there was more time, I would have told how DC-AC converter can be modeled. There I would have shown multi-level converters, but it can be done. Yes.
Hello, sir. Good morning.
Good morning, sir.
Sir, this is Rajesh from SIT.
Yes, sir.
Sir, actually, I have done some literature survey on converters associated with PV.
Okay.
Sir, I have gone through that. Some boost converter associated with PV having little difficulties like discontinuous in output current.
Okay.
Sir, because of that, so is it suggested that converter is as suitable for PV application, sir? Or
Sir, actually, if you see the literature, yes, the Cock converter, there is something called a zeta converters. There are so many converters that they use.
yes.
But the thing is, sir, what I have observed is, see, these converters, they have this what you call as discontinuous mode, right?
Yes.
That depends on the load that you have applied across the converter. Say, for example, you have a boost converter here, and you have a PV here,
Yes,
right?
sir.
Now, what happens is if the load is very, very less, what I'm talking is high resistance. Low load means high resistance.
Yes,
If this is very, very high, then not just boost converter. What happens is even the Cock converter or other converter will be your output, your converter will enter into discontinuous mode.
Okay, sir.
So what you should basically do is you should have a fair idea about the minimum and maximum values of R. Right.
Okay.
Suppose you've connected it to an inverter. Okay. If you connected to an inverter or something, you should be able to model this as an equivalent R.
Okay,
now, if you can come to know, say, for example, R is varying from, say, equivalent is varying from 20 ohm to 300 ohms.
Okay.
Then for a design inductor and for a given design L and C, whether 300 ohm is taking it into discontinuous conduction mode. If this is happening, then you have a problem.
Yeah,
I think using a Cuck or a SEPIC converter, the range for which the converter remains continuous, maybe much more than a boost converter. That's possible. That's why they must have told SEPIC or a CUC converter should be used.
Yes, sir. That is, but inherently that boost converter is giving a discontinuous output voltage based on the operation of converter, sir.
Maybe that is because of that load, whatever load that they have.
Yes, sir. Maybe that is because of the load.
Yeah, maybe. Yeah, it is possible. That's why we do always a worst possible design, right?
Yes, sir.
So if you can take example, the worst possible is 300 ohms. I'm going to make sure that the inductor behaves, works in continuous conduction mode during this time. Yes, your boost converter will then work in continuous mode. Only thing is your inductor size might be much bigger.
Much bigger, yes, sir. That's
but that's possible. It's possible to have boost converter is continuous. Probably it might be a bigger inductor.
Bigger inductor. Okay.
You can write an F file like this and find out.
Okay, sir. One more question, sir. Sir, in a buck converter, actually, so there will be a diode now, sir, in parallel, means in anti-parallel to the load connected. So while moving from one mode to another mode, sir, means one switching on to switch off mode, or I'm coming from back to switch off to switch on mode.
Right.
So then if I close the switch, diode is having some reverse recovery characteristics. Recovery. So how can I avoid that short circuit, sir? That small microseconds is enough to give short circuit across the diode, right?
Yeah, that's why what they do is they go for synchronous buck.
Synchronous. If I use diodes, sir, can't I rectify that problem?
You can do it. It again depends on the power level. If your power level is low, it's fine. See, usually what I'll tell you, if your industry approach is simple, they just override the diode.
Okay.
Right? You override the diode, a little bigger component you put, it's fine. Otherwise, you have to go for soft switching technique, something like, how resonant converters and all are there. So that you just make di by dt or dv by dt lesser.
Okay, sir.
Usually what they do is to avoid these problems, these problems keep coming every now and then. So what they do is they overrate the components and put it.
Overrate, sir, overrating the component.
Yes, overrating the component. See, for example, if that reverse recovery current is huge, right? If the diode cannot withstand it, see, usually we don't consider that, right?
Yes, sir.
Then your diode will destroy. So what you do, you overrate the diode. You put a little bigger diode. That's what they do in industry.
Okay.
Right? Yeah.
Okay, sir. Thank you, sir. Thank you very much. Sir.
Yeah.
Hello.
Yeah.
Anyone else is there? I think one more fellow has dropped in a chat box. Can we do stability analysis?
Yes, you can do stability analysis. Stability analysis you can do using you can write small signal models that can be done. Yes, I can send some material if I get the email ID. If someone wants it, you can drop in your email ID. I will send you some starting materials for stability analysis.
Okay. Anyone want to ask anything? Thank you to the presenter for your informative session, sir. Thanks to the organizing team. Thank you, Sharavanan, sir. Okay, thanks. It's a good session. Okay, I think no one has dropped any doubts till now. Anyone among the participants? If you have anything, you can ask. You can ask to our speaker. Okay, Arjun, I think we had a good informative session starting from the modeling of basic RL, RLC circuits and how we can implement the same, how we can do analytical approach for the same approach for developing the converters and also MATLAB simulations, MATLAB coding and output.
Yeah.
It was a really informative, and who wants to start their research or work in power electronics, who wants to come in from basics, it's really a good information, and you have given a very good insight out of it. Thank you very much.
Thank you.
Thanks a lot for being so patient and very clean explanations you had given. Very smooth, very no much hurry. Such a nice explanation you had given, sir. Thank you very much, Arjun, sir. On behalf of Department of Electrical and Electronics Engineering, And on behalf of SIT College, Complete Institute, on behalf of the Institute, I wholeheartedly thank you. I will convey my thanks to you, sir. And we look forward for you to be for more connection with us.
Yes,
Like
yes.
this kind of sessions, guest lectures, FDPs, we can have some more interactive sessions like this in the future coming days.
Yes.
It's a
Yes.
great opportunity for us, even for us to review our basic ideas and the things
Yes.
and all. Thank you very much, Arjun sir, for
Thank you. Thank
this
you, Rajiv,
interactive
for the
session. Thanks a
opportunity.
lot.
Thank you.
Thanks a lot.
Yes, yes,
Okay,
yes.
can we conclude the session? Do you have anything
Yes.
to quote? Do you have anything to quote for our participants at last
The
quote?
thing is that, see, my email ID and mobile number
Phone
is
number.
displayed on the screen, so you can always get back to me, right? Together only we can always, build things, right? So
Yeah.
whatever I know, whatever experience that I have from my laboratory, I will be always ready to share with you, right? You can always reach to me for, say, if you want any research if you want to, help any regarding any research proposals or anything for that matter, maybe help with your problem statements. How do you devise? What is the worst condition that you always take into care? What is the safety factor that you should always consider when you make your research statement? Anything for that matter, any discussions, it is always welcome.
Oh,
right?
Thank you.
Thank you
Thanks
so
a
much.
lot, Arjun.
Yes,
I'm
thank-
concluding it. I'm
Yes,
concluding
thank
it.
you.
I'm
Thank you,
ending the
Raj.
meeting.
Yes.
Thanks a lot once again.
Thank you.
Okay, fine.
Yeah, bye.